One of the more aesthetically pleasing sights in nature is the structure constructed by bees to form the basis of their home, honeycomb. The concise and orderly pattern of comb is a symbol for structure, order, utility and strength, and with good reason. This pattern hasn't occurred by accident. Let's discuss this shape from civil engineering point of view, where optimization and serviceability are the main criterion to be fulfilled. How strong is honeycomb? The hexagonal cell is very strong, in relation to the weight the wax used. Honeycomb of just 100 grams can support weight of up to 4 kg, an amazing ratio. Hexagonal honeycombs. When bees build honeycombs, they do so in a pattern of tiled hexagons. They create the borders of the hexagon with wax, leaving hexagonal holes that they can use to store honey, pollen, or eggs. But have you ever wondered why bees use hexagons? Why not use a simpler shape, like squares, triangles, or circles? There is likely a simple physics-based explanation and maybe a little math. Let's take a deeper look. The quick answer is that the hexagon is the single tileable polygon that has the least perimeter for a given area. This is important because bees have to spend a lot of energy to make the wax for the borders of each honeycomb cell. Less perimeter means less wax, and less wax means less spent energy. Let's examine the math behind the claim that the hexagon is the single tileable polygon has the least perimeter for a given area. First of all, we must show that there are only 3 regular polygons that can be tiled: the triangle, the square, and the hexagon. Secondly, we must show that out of those 3 polygons, the hexagon is the one with the least perimeter for a fixed area. However, in order for a regular polygon to be tileable, its interior angle must also divide evenly into 360 degrees. The largest factor of 360 degrees is, which is too big to be an interior angle of a regular polygon. The second largest factor of is, which is also too big. However, the third largest factor of is, which is the interior angle of a regular hexagon. The fourth largest factor is, which is the interior angle of a square. The fifth largest factor is, which is not the interior angle of any regular polygon. And the sixth largest factor is, which is the interior angle of an equilateral triangle. After this, the factors of 360 degrees are less than 60 degrees, which are too small to be an interior angle of any regular polygon. So the triangle, square, and hexagon are the only regular polygons that can be tiled. Consider a regular polygon and then sides inscribed in a circle with a radius of r. The polygon can be divided into n triangular slices, and each of those slices can be bisected at each central angle, making 2n. Area of triangles r. So r can be derived as, substituting r in p, putting value of n as 3, 4, 6. Therefore, the hexagon has the least perimeter for a fixed area. We have shown that the hexagon is the single tileable polygon that has the least perimeter for any given area. But in a honeycomb grid, the perimeter of each cell is actually a wax border with its own width that is shared by adjacent cells, and this may affect our assertion that the hexagon is the most efficient shape. So to be thorough, we need to consider the wax-to-honey ratio for each tiled shape. We will consider the potential candidates of the triangle, square, hexagon, triangular honeycombs. Let's say there is a type of bee called the triangle bee that builds its honeycombs with equilateral triangles. The triangle bees make wax walls that have a width of W that will separate each honey cell with an area of A, and sides of S. And by the nature of the triangular pattern, the wax walls will meet in hexagon shapes. The wax-to-honey ratio for the whole honeycomb would then be the same as one individual triangular tile. The wax walls for one tile consist of 3/6 of a hexagon and 3 rectangles, and so its area W would be since the area of an equilateral triangle. Solving for S would give us Substituting back into W would give us W. The wax to honey ratio for the triangular beehive is then square honeycombs. Now let's say there is a type of bee called the square bee that builds its honeycombs with squares. The square bees make wax walls that have a width of W, that will separate each honey cell with an area of A and sides of S, and by the nature of the square pattern, the wax walls will meet in square shapes. The wax to honey ratio for the whole honeycomb would then be the same as one individual square tile. The wax walls for one tile consist of 4/4 of a square and 4 rectangles, and so its area W would be. Since the area of a square is, solving for S, would give us, and substituting back into W, would give us. The wax to honey ratio for the square bee is then hexagonal honeycombs. Now let's say there is a type of bee called the hexagonal bee that builds its honeycombs with hexagons, like regular bees. The hexagonal bees make wax walls that have a width of W that will separate each honey cell with an area of A and sides of S, and by the nature of the hexagonal pattern, the wax walls will meet in triangular shapes. The wax to honey ratio for the whole honeycomb would then be the same as one individual hexagonal tiles. The wax walls for one tile consist of 6/3 of an equilateral triangle and 6 rectangles, and so its area W would be. Since the area of a regular hexagon is, solving for S, would give us, and substituting back into W would give us. The wax to honey ratios then. Real honeybees build honeycomb cells that are an average of 4.85 mm wide, which gives a honey area of 81.484 square millimeters with wax walls that have an average thickness of 0.5 millimeters. Using these values, we can use the formulas above to calculate the numerical wax to honey ratio for each shape, which means that the average honeycomb, made up of hexagons, has a 10.575% wax to honey ratio. If the reason bees make their honeycombs in a hexagonal pattern rather than some other pattern is not because of natural selection, then it must be because of some innate instinct. But where did that instinct come from? The only plausible explanation is that it came from an intelligent designer. Bees build their honeycombs in the efficient hexagonal pattern because of an instinct that was put there by the same God who created the geometrical laws of the universe.